Okay, 37-year journey to the sun sounds a bit strange, I know. Obviously, it marks the number of years I've been at Rutherford. And I should say thank you for that introduction, by the way. And yes, I did decide to retire, but hope not to disappear completely, of course, as you say. But the idea is not just to talk about me. The idea is to say something about how things have changed here at Rutherford, within the missions, within the science, and the capabilities, if you like, within solar physics, which is the area that I work. So again, it's not just about me. I came to Rutherford 37 years ago, and I came to join a team that was to work on this beast, the Solar and Heliospheric Observatory, SOHO for short, which had been selected as a cornerstone project for European Space Agency to study the sun in great detail, both internally, the surface of the sun, but also the area of space coming from the sun, if you like, the heliosphere, as the solar wind heads towards the Earth. It was to be the big international solar observatory in solar physics, if you like, that was to dominate the next few decades, to be perfectly honest. And I came to work with a team that was being established at Rutherford because the mission was accepted and people were beginning to write the proposals. And I joined a chap called Bruce Patchett, who was the principal investigator for the instrument that was being proposed. A wonderful man, technically brilliant, wonderful sense of humor, brilliant to work with. And he had an equally excellent project manager called Eric Sawyer, who could even be in the room for all I know. And they were a wonderful team to join. And I was the project scientist, and the three of us, it's quite quaint when you consider what we do now. I was the only one that actually had a computer terminal in his room of the three of us. So we sat around my computer terminal with me doing the typing while the proposal was written between the three of us. So it was actually quite an interesting time, and one that I do remember fondly. It was successful. The proposal was successful, involved a large consortium. Again, this is not all about me. Solar physics is a big international thing, and we had a large consortium. And the instrument flew successfully. It was launched aboard SOHO in 1995. And I had the honor from 1992 onwards to be leading it. I was the principal investigator, in fact. That's actually Bruce Patchett in the middle of that picture there. Some of you might remember him. Lovely man, as I say. Unfortunately, he died around 1997, I think it was. So we lost not just a great technical leader, but also a great friend. But I want to draw your attention to the chap on the left-hand side. Some of you will certainly know him. His name is Alan Gabriel. He's still around. I've known him for years and years and years. And the reason why I pick out him is that he was part of Bob Wilson's group that came from Harwell. They were involved with the Zeta machine, which was the fusion machine, but they were using the plasma diagnostic techniques that they were using on that machine to try to devise instrumentation that could fly in space, not to just do plasma diagnostics or something in a tank, but to look at the sun and say something about the solar atmosphere. And that was very much the beginning of the solar program that we have now. In looking at Alan there, you're looking at one of the pioneers in a sense. That's what I'm trying to get at. And along with Bob Wilson, but also equivalents at the Mullard Space Science Laboratory, University of Leicester, University of Birmingham, and the other groups. We had a set of pioneers. And for people like me that are retiring now, we came after those pioneers. So I had the honor really of being able to work with people like Alan and the other pioneers, the ones that have really broken the ice, if you like, set up the scene, done the things first so that people like me could actually come in and have a solar physics career, flying with instrumentation in space and within a framework that people like Alan had set up. And I think it's really important to shout about that and say we had some real heroes in a sense who led us. But if you like, this isn't Alan, by the way. This doesn't need introducing in many ways. If you think of not just my timing, if you like, I'm jumping back a little bit here, but given the age that I am, obviously, yes, I met these pioneers, if you like, but also I was old enough to be inspired by this, of course, and a lot of us were, I suppose. There are probably some others left in the room. Those of us that are approaching retirement, not just lived through Apollo, but we were able to absorb it, to really enjoy it, to get into the details, if you like, and it was a huge inspiration. It wasn't a thing that started my interest in space, that came even earlier, but it was a real kick, if you like, to say, yes, you want to go in that direction for your career. And yes, it's over 4 decades. I started at Birmingham with a PhD in 1979. Yes, I'm that old. So that's 44 years ago. They're the 3 institutes I've been at. over the years, high altitude observatory in Colorado before I came here. But the missions, the launches there are the three mainstays, if you like, of my career in a sense. The one on the left-hand side is Solar Maximum mission, launched in 1980. The Solar and Heliospheric Observatory that I've already mentioned in the middle, launched in 1995. And so Stereo on the right-hand side, which is two spacecraft launched in 2006. More about those later. So in 1980, this is what we had. This was the sort of the world's fleet of spacecraft looking at the sun at that time. It was the Solar Maximum mission. Clearly, I'm going to put a now in a while, but this is what we had. In those days, the operations for that spacecraft was in the Goddard Space Flight Center, a NASA facility. That hasn't changed. We still do that. We operate things from there. But I was part of an operations team for that instrument, for one of the instruments on that spacecraft. And we had briefings each day from a group from the Space Environment Lab. They would put up pictures like the one in the middle at the bottom there. We had sketches in front of us at the beginning of the day to do the planning. We'd choose which bits of the region of the sun we want to look at, because we couldn't look at the whole sun with the instruments that we had. We only had a part sun image or field of view. And you'd actually be hunting flares. That's what we were looking for, the explosions in the sun's atmosphere. There's a spacecraft, by the way, in the back of the shuttle. It was repaired in 1984. That's the first thing to be repaired in space by the shuttle. But I won't dwell on that because of the time. But we were using those images in the briefing as part of the planning team to decide where to point. Invariably, we'd point to an active region, sunspot region, sun's atmosphere, where we'd think there'd be lots of flares, and of course they'd occur somewhere else. And that always seemed to happen, in my opinion. But I got interested in the imaging of one instrument that wasn't looking for flares, and it was a coronagraph. And this is one of the images from that coronagraph. Obviously, this is an old image. It blocks off the sun, basically, so it can actually see around the sun and pick out things like the structure that you can see there, which is a huge eruption coming out of the sun. It had only been discovered a handful of years earlier. You can see something that looks like a big bubble with a void behind it and a bright mass behind that. It's pretty clear early on these involved the eruption of about 1 billion tons of matter from the sun in one go at speeds of up to a couple of thousand kilometers per second. I was trying to understand what's happened below those things, just talking about a tiny bit of research there. So I was looking at using some X-ray instrumentation, in fact, in conjunction with the coronagraph to look underneath. Now, I look back at my papers now, and these look quite quaint, actually. These are the days of the pen plotters and the cartoons and things like this, and even sketches. You know, that one on the left, those are sketches you see there. That's trying to, okay, you have sort of traced over the image or whatever to produce that. You'd never do that in your papers now. But in those days, that was the thing to do. And in a sense, the illustrations I'm showing here are not silly. I mean, this is how it was. And in particular, the one on the right-hand side, we were trying to identify, there's a big understanding that the things that were driving these mass ejections, they're called coronal mass ejections that you see there on that image, were actually driven by flares. They were responses to the explosions in the sun's atmosphere. And the observations from X-rays, really simple experiment. There are times when you have a simple experiment which just puts two things together, and you don't need any modeling. It just shows you that what was being suggested wasn't actually right. In this particular case, that was the case. The flare wasn't there in many cases, or it was off to one side, or it occurred after the event, or it occurred before it. There was seemed to be an association between flares and these things, but it was a real complex thing. It wasn't anything like what people were suggesting. So, you know, the simple things often are actually some, you know, really exciting in a sense to actually show something so basic like that. But looking at the sun then, we're talking about our star, of course. It's the only star you can study in phenomenal detail. And I'll show you some observations later on. I hope I'm going fast enough to be able to do that. So we can study the sun as a star, if you like. It's the star we can see them most clearly. So we can study stars, all stars, if you like, processes in all stars. We can study plasmas in conditions we can't recreate on the Earth, but we can also study the sun because we're interested in how the sun impacts the Earth, because it does. And we often talk about space weather and impacts on human assets and human activities. And I suppose that's why I'm in the resilience section of this talk here. So everything I'm talking about here has relevance to that. So where are we now? We have this strange strategy in a sense, because it's like a global strategy and it looks great because it looks so well organized in the way that it's structured, and in the way I'll describe it in a second. But it sort of came about bit by bit. You can see SOHO is still there sitting in the middle out in front of the Earth. It actually doesn't orbit the Earth, it orbits the L1 point in front of the Earth, the Lagrange L1 point, which is where the gravitational pull of the Earth and the the sun form a balance, and you can orbit that point, which is rather strange, of course, but it means you can sit out in front of the Earth all of the time, 24 hours a day, 7 days a week. You can image the sun, you can sample whatever's passing over the spacecraft. Lovely place to be. Well, not for a person, of course. And on the right-hand side here, you've got two big observatories, the Solar Dynamics Observatory from NASA, the Hinode spacecraft from JAXA from Japan. All of these have UK involvement, by the way, in different ways, except maybe one. But SDO and Hinode are, think of them as the big imagers, the ones that need huge amounts of telemetry, large instruments, and you're going to have them in Earth orbit. But if you think of those spacecraft, which are wonderful spacecraft, they all have the same view we've always had. Humans have always looked at the sun from the direction of the Earth, if you like. So we kind of left the cradle with the launch of the stereo spacecraft. These two spacecraft, I don't know where it's clear from the image there, but they orbit the sun. They took off and went out sideways, if you like. And the idea of that was you could look back at the Sun-Earth line. So you could study the sun, you could look towards the Earth and see what's flying between the two, if you like, in a way. You know, think back to that coronal mass ejection picture. You saw that from the side. If that was coming towards you, it's not so easy to pick out in quite the way you want to. So it's good to be out from the side. And the ones on the left-hand side, Solar Orbiter and Parker Solar Probe, those are the encounter missions. We're now heading towards the sun. We're not going to land on the sun, well, presumably not. But these two are the encounter missions. They're getting close. Solar Orbiter was launched in 2020. Gets closer to the sun than Mercury. And even from that distance, they can image the sun in a way that is phenomenal, the closest imaging that we have. I also list Parker Solar Probe here, which doesn't actually image the sun, so it's a bit of a cheat, but this is a NASA mission that actually gets close enough to literally slice through the outer part of the sun's corona. It has one instrument looks out sideways, the rest are sampling the environment around the spacecraft. So two of these, I had the honor to lead instrumentation. I've already mentioned that, and yes, that is me standing in front of the launch pad. But on the right-hand side, you can see the engineering model of the instrument to give you an idea of the size. And the picture there of the Goddard Space Flight Center, yes, it was the same as SMM in that sense, but the operations facility was more like mission control in a sense. If you think of Apollo days, in a sense, you got all the terminals, you got access to all the data, you got all the people together, you got sophisticated planning tools. It's a really, completely different approach to life, taking advantage of all the advances in technology and day-to-day planning, real access to your instrument. It was a wonderful thing to be able to do. I also stress stereo because I had the honor to lead the instrument there, and that's the stereo team. A few of the members are actually in the room. But one thing to highlight here with stereo, I'll show you some images in a minute, but there is an image on the right-hand side that I'll describe some. The instrument is an interesting thing to look at there. There's a mock-up of the instrument there. The SOHO instrument, you can almost sit, it's a 100-kilogram instrument. You could almost hit it with a sledgehammer and it wouldn't care. I'm exaggerating, of course. The stereo instrument is a real lightweight thing built a decade later, a completely different approach to life, much smaller as well, of course. Obviously doing a very different thing, but just witnessing the change in the approach to the instrumentation is really quite an interesting thing when you're doing that. Now I'm going to just indulge completely by going through, if I've got enough time to do so, just a few of the observations, give you a flavor for how solar physics has moved on. But stress again, it's not just me. There's a lot of people behind these things for different instruments and spacecraft, and obviously this is the area which, if you like, I know and love. You're looking at the sun here, for example, actually from the Solar Dynamics Observatory, and you're seeing a set of active centers here, active regions where there would be sunspots, but you can't see them in these images. These are extreme ultraviolet light, and you can see how you can see magnetic field structures in the sun's atmosphere. That's what the loops are. And they're visible because they trap bright plasmas that are emitting in ultraviolet wavelengths that the instrument is sensitive to. And it shows you how dynamic and dramatic the sun's atmosphere is. Nothing like our atmosphere, of course. And it's almost no surprise that elements of that atmosphere just erupt and explode to produce the flares and the coronal mass ejections. A lot of plasma physics in that, of course. There's no way I can talk about all that. If you want details, grab a solar physicist when you're out there. There are a few of us in the room. Or solar and heliospheric physicist, a few of us in the room. This is a view from Solar Orbiter. And it's the same sort of thing. It's the plasmas in the sun's atmosphere, but low solar atmosphere here. And you can see the plasmas actually trapped in the fine-scale magnetic structures in the sun's atmosphere like we've never seen before, in a sense. These sorts of observations are beautiful. And you're looking for the plasma processes that occur in that atmosphere, the little explosions, the little the places where things change, the magnetic fields can even reconnect, and you get acceleration of plasma into space to form the solar wind. This is the bed of that, if you like, the place where it all happens, right deep in the sun's atmosphere. Moving out, how's this for an explosion in the sun's atmosphere? You know, you kind of think of the sun being, or most people think of the sun as just being inert in a way, but this is one of the biggest eruptions in a sense. You almost don't know what to call this one. In a sense, it's a cross between what we call prominence eruption, but also it involves a coronal mass ejection, the thing you saw earlier. Often they go together, but there's a lot of stuff raining back down on this one. It's a really dramatic event. And this is more up-to-date coronagraph observations, but the sun has been put in the middle as well to show what it looks like from another instrument. But you can see the eruption of these coronal mass ejections, which we're monitoring every day now from a space weather point of view to try to understand when they're heading towards the Earth. What about the view sideways then? This is from stereo. For this particular one, these are differenced images, so they look black and white because you're showing enhanced and depleted material. Oh, 2 minutes, right? I'm just going to run this. What you're doing here is effectively seeing the structure of material moving out from the sun. And you can see the coronal mass ejections on here, but on top of that, you can see that down there near the sun, you've got a really complex, violent place, if you like, where there's a lot of stuff flying out from the sun in different structures. The sun is continually spewing stuff out into space, if you like. And this is defining the environment that we live in. And talking about that, these are stereo images again. They're not different in this case. You can see the stars, obviously. You can see the sun. The two images are from cameras way apart from one another, either side of the sun, looking back across the sun-Earth line. And the right-hand one, that bright star on the right-hand side, is the Earth. So you're on that. When I run it, you'll see a comet going through, but you've got to try and ignore that because he's just trying to steal the show. That's Comet Pan-STARRS. What I want you to look at is the fact that you can see the coronal mass ejections come out, and during that period, at least 2 of those passed right over the Earth. On the one on the left-hand side, is you can see the planet Mercury, in fact. But these really show our place in space. Just to finish off then, if you go over to R100, I don't know whether everybody's going to do that, you'll see a display like this. I think it's a different version now. And if you include the ground-based stuff, the history of the missions and projects of this place goes back, you can go back to 1930 with the Ionoson, for example, but these are the space missions on here. And it's quite an impressive record of missions and instruments that have been flown into space. Frightening thing for me is I've mentioned those missions that I have had significant involvement with that go back to Solar Maximum Mission, SOHO, Stereo. I've been involved with a lot of the others as well, but these have been the major ones, if you like, and also with the beginnings of Solar Orbiter. And the thing that's frightening to me is the way those sort of span the time span of this organization, which I find terrifying. But it's been a very interesting journey. I hope that's been an interesting illustration of how things have changed. And yes, that is a real image of the sun taken in 2022. So thank you. Thank you. No question.
I think you know, for me, listening to your story brings together a lot of threads from the other talks, actually. With Chris talking about the UK being a world leader, clearly, thanks to the efforts of yourself and the teams around you, I think the UK can genuinely claim to be a world leader in solar physics. But as you point out, it is a team sport. It is about being open and collaborative. And one of the things about Richard is that he epitomizes that spirit of collaboration and cooperation, not just nationally, but internationally as well. And that's one of the reasons why Richard and his programs have been so successful. So that's picking up on a lot of the themes around inclusion as well. So are there any questions from the floor first? Rick.
Hi, Richard. Fabulous career and a fabulous talk. Thank you. So I'm going to be really nasty now, and I'm going to ask you what your proudest moment from your career has been.
Good grief. That is difficult. I suppose, if I'm honest, well, I don't know, I'm just grabbing something in a way. With SOHO, I think there was a change. While we were putting SOHO together and defining how SOHO would work, the one thing I pushed for was that we should be really inclusive in the sense that we should have an operations capability that meant, if you like, the community could come in and actually use things. We even had an operations room here where people could come along and join in the planning. They could even run an engineering model from a computer terminal and run what it is they wanted to see run in space for their observations, and then take part in the planning in a sense, and even see their data the next day and so on. So we never kept the data to ourselves in a way. It was always totally open. And I'm kind of proud of that. As part of that, even as principal investigator, I didn't demand to be on every paper. I'd have hundreds of papers I didn't even know anything about. But I think it's the way we should play it in a sense. You're paid by public money to build something like that. I mean, I didn't build it. I'm not the engineer or the technical person. But I think the point is to let everybody play with what you're building in that way is the important thing. I think that's one of the things I'm proud of. It does mean that I think the instruments are very well exploited, if that's a good way to put it.
Any other questions from the floor?
Hi, Richard. Thank you. Very interesting presentation. Where do you see things going in the next sort of 10 to 20 years? What more needs to be discovered from a solar physics point of view?
Good grief. I mean, there are two sides to that. One is the space weather side, which is research as much as anything else, because we do need to understand the impacts on the Earth, and it is part of the National Risk Register, space weather and its impacts. It is something where there is a facility at the Met Office to make sure that the UK is forecasting these things along with other groups such as in Boulder, Colorado. And we need to understand how to feed into that properly and understand, if you like, feed in the research to learn how to predict and track and all the rest of it, and understand the onsets of things that are going to impact us. So that is research linked to operations, if you like. But in terms of understanding the sun, for example, I showed that strategy. The one thing that's missing from that, in a sense, is to go up and study the solar poles to understand how those fit in. And that sounds like a strange thing to do, but it is, for people not familiar with the sun, it's probably best to look at the Earth and say, well, you wouldn't orbit the equator of the Earth to study how the poles of the Earth look, how they work or what they look like and so on. So there is a bit of a gap there. Solar Orbiter is climbing out of the ecliptic plane, or will do. But there are certainly future possibilities for doing that right over the poles of the sun. I know Ulysses flew over the poles of the sun, but didn't have any imaging capability of the sun itself. I'm sure I could list lots of other things. I mean, there are lots of lovely possibilities that people come up with for future missions, but I think that's probably enough for now. Thank you.
At least another career's worth.
Oh, yeah.
Yeah.
Sure. Absolutely.
Right. Thank you. I'm afraid we can't get to the questions online. We have to move on, but thank you very much, Richard.
Thank you.